In this video, we're going to spend some time going over the organization of the periodic table. We're going to focus on what periods and groups are, and we're also going to describe the classes and families in the periodic table. So the periodic table of elements is just a nice table in which we've organized all the elements that we know of today, all 118 of them. As we mentioned before, there's 92 that are natural and 26 that are synthetic. And the scientist who essentially used all the properties of the elements to organize them the way they are was Dmitry Mendeleev. Now, he wasn't the only one to organize elements in a nice logical way, but what he was quite known for was the fact that he could make predictions. So even elements that he did not know, based on the way he was organizing his periodic table, he could predict the properties of those elements even before they were discovered. So based on the area that he placed those elements, so he could predict the mass, he could predict maybe how it might react, for example, or what it might look like. So if you want more information about that, just to see the how amazing that was, the work of science, you could take a look at this video over here. So remember that elements are arranged according to increasing atomic number, so smallest to biggest, from left to right on a periodic table. Elements that have similar properties are typically found in the same area of the periodic table. So the first area of organization that I want to mention is that of periods and groups. So the periodic table is organized into 7 periods. And a period is just a horizontal row. So this is one of the rows over here. Here we have another. And it keeps going up until 7. So there's 7 rows in the periodic table of elements, which means there are 7 periods. And so we can identify where elements are based on their period. So for example, if I want to know what period carbon is in, I find carbon. It looks like it's in period number 2. This is carbon over here, period number 2. Calcium, so this is period 1 this way, period 2 this way. Let's go back, sorry. Calcium right over here. This is period number 4 if we count down, so calcium is in period 4. Aluminum is over here. It's in period 3. It's in the 3rd row. And the neat thing about the period is that it tells you how many shells an electron, an atom would have, how many shells of electrons there are. So if you remember drawing those Bohr-Rutherford diagrams with all those circles and everything like that, where you could put 2, 8, 8, so on and so forth, the number of the shells of electrons is determined by the period. So for example, carbon being in period 2 would have 2 shells of electrons. Calcium being in period 4 would have 4 shells, and then aluminum being in period 3 would have 3 shells. So those are the periods. There are 7 periods in the periodic table, and the period number tells you the number of shells. I just want to clarify something before we go on to groups. So let's go look at our periodic table that we use for the course. You'll notice that this periodic table has 7 periods, 7 rows, counting from here, 1, 2, 3, 4, 5, 6, 7. But then you'll notice that there's 2 more over here. These are not additional periods. There's not 9 periods. These actually belong in here. So we just took them out and placed them at the bottom here, but they actually are part of rows. So the lanthanides are part of row 6, and the actinides are part of row 7. So there's still 7 periods, not 9. Just keep that in mind when you're studying the periodic table. The other aspect we need to look at is something called the groups. Groups are also sometimes called families, but we'll get to calling them families later on in more detail when we describe characteristics of elements. The periodic table has 18 groups, and it's basically your vertical columns. So this is one group, this is a second group, then we have 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So there are 18 groups. And what I want you to get is that over here we have the group number written on top, but if they're not written on top, you need to know that number 1 starts on the left side and 18 starts on the 18's on the right side all the way at the end. So we can identify what group elements are in. So for example, if I look at carbon, carbon's over here. You could start counting from left to right, or you can say, well, this is 18, so this is 17, 16, 15, 14. Carbon is in group 14. Calcium is in group, so here's calcium. Makes sense to start from left to right, so this is group 1, group 2. Calcium is in group 2. And aluminum, over here, you could count from left to right or right to left, so 18, 17, 16, 15, 14, 13. Aluminum is in group 13. Now, the neat thing about the group number is that they tell you the number of valence electrons. This should say electrons there, not electrosen. So this is electrons. It tells you the number of electrons in the last shell. Remember, valence electrons are the electrons in the last shell. They're the ones that are involved in the bonding, ionic bonds and molecular bonds, covalent bonds, I should say. So if you look at the group number, let's say group number 1, an element in group number 1 would have one valence electron. An element in group number 2 would have two valence electrons. So if you look at calcium, calcium has two valence electrons. Now, this rule doesn't really work for the elements in groups 3 to 4, or 3 to 12, I should say. These are an interesting bunch of elements called transition elements. They follow a bit of a different pattern, and we'll go over that later on. But the rule does continue if you go 13, 14, 15, 16, 17, 18. So something in group 13 would have three valence electrons. Something in group 14 would have four valence electrons. So, for example, carbon has four valence electrons. Aluminum has three valence electrons. Something in group 15 would have 5. 16 would have 6 valence electrons. 17, well, 7 valence electrons. And 18, well, 8 valence electrons. So group number tells you number of valence electrons. Just remember, it doesn't work for the elements in groups 3 to 12. So what you do is you do 1 in group 1, 2 in group 2. Skip these, go to 13 and say 13 is 3, 14 is 4, 15 is 5, 16 is 6, 17 is 7, 18 is 8. There is an exception, though. If you look at helium, helium only has 2 electrons. So it doesn't make sense for it to have 8 in its last shell if there's only 2 there. So helium is that exception for group 18. It only has 2 electrons in its last shell. But you might remember from grade 9 and 10 that these are the noble gases, and they have a full valence shell. So even though it's only 2 for helium, it still counts as having a full valence shell because it's that first shell. So just remember that as that pattern when you go back to review the idea of group number and valence electrons. So you should be able to answer questions like this, defining a period, a group, describing the periodic table based on number of groups and periods it has. If I give you an element, can you find the group number and period number? If I tell you group number and period number, can you find the element? So let's do an example like that. We've already done some like this here. Here you just have to define and just locate, but here we're going to try to find what element we have in group 2, period 3. So we'll go back to our periodic table. Here we have, so group 2 we said is over here. Period 3, so this is 1, 2, 3. Group 2, period 3. Whoops, let's go back here. This is group 2, and then period 3 over here. So the element that's in group 2 and period 3 is magnesium. So if I give you both group and period number, you should be able to figure out what element is at that spot. You can pause the video and try number 6 yourself. So group 16, period 2. Group 16, period 2. Okay, let's go back here. So group 16, it's over here. Period 1's on top. Period 2 is over here. Group 16, period 2 is oxygen. And then from that, you can figure out the number of shells and valence electrons. So for example, magnesium would have 3 shells because it's in period 3, but 2 valence electrons because it's in group 2. Oxygen would have 6 valence electrons because it's in group 16, and 2 shells because it's in period 2. So now that we've seen groups and periods, we can go and see other organization in our periodic table, the way the elements are organized. Elements with similar properties are in similar areas of the periodic table, or in the same areas of the periodic table. So here we can see we have three different colors. These three different colors are the three different classes of elements. You can think of them as the major categories of elements that exist on our periodic table. The three major categories or classes are the metals, semi-metals, and the non-metals. Semi-metals are also called metalloids. That's how they're more commonly called, metalloids. So they're oftentimes color coded. So, for example, here you can see the ones in red, the boxes in red are the metals. There's a lot more metals than there are all the other elements. The ones in green are the metalloids, and the ones in yellow are the non-metals. So, for example, carbon is in yellow, so it's a non-metal, whereas beryllium is in red, so it's a metal, or germanium is in green, so it's a metalloid or semi-metal. You'll notice that metals are typically on the left side, non-metals are on the right side, and metalloids are sort of in between them. There is one exception for the non-metals to remember, is it's hydrogen. Hydrogen has certain characteristics that sort of place it on the left side, but it is a non-metal. So hydrogen is considered a non-metal, even though it's placed on the way on the left side with the rest of the metals. Just remember that as one of the exceptions. So again, three major classes are metals, metalloids, and non-metals. You need to know the physical and chemical properties of these three major classes, and we'll briefly go over them. So this is a periodic table that has not been color coded. On the next few slides, you will see some color coding instructions. You can go ahead and do that to get practice, but I'll show you a couple tricks to remember where metals and non-metals are without having to, color a periodic table in every single time. So first we'll go over the metals. Here we have some examples of metals like sodium and gold. So here's sodium, color-coded in red there. And then we have our gold over here, also color-coded in red. So if you were to color code them, you would find that you're coloring about 93 elements that are metals. So in terms of physical properties, metals are typically lustrous, so shiny. They're usually good conductors. They're typically ductile, so you can stretch them into a wire, and also malleable. They're usually solid at room temperature and have a higher high density. The exception for being solid at room temperature is mercury. Mercury is a metal that's actually liquid at room temperature. So mercury is Hg. It's a metal that's liquid at room temperature, but the other ones are all solid at room temperature. In terms of color, most of them are a silver color or gray color. There are exceptions like copper and gold, for example. They have different colors, but the majority are silver, grayish. And so all these characteristics that I'm describing here were used to place these elements in their location on the periodic table. In terms of chemical properties, there are many metals that are reactive with water. Many can rust easily when they're exposed to oxygen and air. They all vary depending on where they are in the periodic table, but these are some of the most famous or known properties of certain metals, and we'll go over that in more detail shortly. Metalloids. Metalloids are sort of in the middle, in between the metals and the non-metals. And these are the ones you would be color coding. The metalloids can actually be remembered by a staircase. So there's a staircase that you can use to remember the metalloids. And I'm going to show you that over here on this periodic table. So here's our bolded staircase. So you can see over here that we have boron, silicon, germanium, arsenic, antimony, tellurium, polonium, and astatine. These are all examples of metalloids. And so if you remember this staircase, if you put that in your periodic table, then you'll remember where the metalloids are, and therefore you'll remember that the metals are on the left of that and the non-metals are on the right of that. So remember the staircase, and then you don't have to color code a periodic table every single time. So metalloids, typically they're solid at room temperature. They are usually shiny and gray in color. They're not the greatest conductors. They're not as good as metals, but they're not the worst conductors, not as bad as non-metals. So we sometimes call them semiconductors, and their density is in between that of metals and non-metals. So physically and even chemically, some of them will act like metals. Some of them will act like non-metals. So they have properties somewhere in between that of metals and non-metals. So just keep that in mind. They're in between metals and non-metals on the periodic table, and their properties are in between metals and non-metals on the periodic table. Some resources will tell you that polonium and astatine are not part of the metalloids, but for us, we're going to consider them part of the metalloids. They vary depending on the resource or author that you're reading. And then lastly, we have the nonmetals. So nonmetals, these are all the ones you would be color coding if you want to practice it with color coding. Most of them are gases at room temperature. There are 11 of them that are gases. Some of them are solid at room temperature, about 5, and then one is a liquid at room temperature. And I'll show you how to identify that on the periodic table that we use for our course. Usually they're dull, they're typically brittle, so they're not ductile, they're not malleable, and they're usually pretty poor conductors and they have lower densities. And their chemical properties vary depending on where and which nonmetals you're looking at. Some are highly reactives, and some are not. So, for example, we know that the noble gases, these are nonmetals that are not reactive at all. They're very inert. They don't react. So again, remember that staircase, and you can remember the location of your metals and your nonmetals and your metalloids. So before we do some practice questions here, I want to go and show you your periodic table that you use to show you how you would tell if something is liquid or solid or gas at room temperature. So if you look over here, we have the elements. You'll notice that they have different colors for their symbols. So the colors will tell you what their state is at room temperature. So if you just have the black text, that's going to be solid at room temperature, at the temperature at the room. Whereas over here, if you have blue, for example, you'll see mercury is blue. That's liquid at room temperature, and same thing over here. Bromine is blue. That's liquid at room temperature. And then when you see red, well, yep, that's right. That's gas at room temperature. And so let's just go on and take a look at our noble gases here. So gases at room temperature. Here you can see the staircase to remember where our metalloids are. Remember where your metalloids are, and then you'll remember where your nonmetals and metals are. So another very important characteristic I need you to understand about these classes is that the properties of the elements that we study will determine what we use them for in society. So for example, let's say we want to make a wire, right? Wires around the home, they conduct electricity from one place to another. So a good material for a wire would have to be ductile, so you could stretch it into wire, malleable, and also be a good conductor. So that being said, which class of element would you go pick from to make a wire? Metal, non-metal, or metalloid? Hopefully you're going to decide that a metal would be the better option because metals, they are often good conductors of electricity, and they are also ductile and malleable, so you can actually stretch them into a wire without them breaking. Why would nonmetals be a poor choice for materials to make a wire? Well, try to think about why. Pause the video. Understand that nonmetals are typically bad conductors and they're brittle. So you couldn't really stretch them into a wire. They're not malleable. They'd probably break if you tried to do that. So they don't fit the criteria that you need for a good wire. And you can see some other examples here. It's a gold for jewelry, right? Gold's probably a good idea for jewelry because it's lustrous and it looks nice, right? And it's gold is also soft as a metal, so you can actually mold it into different shapes. And aluminum, you probably wrapped aluminum or sandwiches in aluminum foil before, and it's great for that purpose because, well, it's malleable, so you can compress it and pack it and wrap your sandwich up without it being brittle and shattering when you wrap your sandwich up. So just understand the big idea in these few slides here is that the properties of an element will determine what we use it for in society, right? So if we need a wire, well, we're going to choose an element that is a good conductor and is ductile. So those properties make metals good for being wires, for example. And you should be able to answer questions like this based on the last slides that we saw. So lastly, in our organization, we want to take a look at classes, at families. So classes were the major categories: metals, nonmetals, metalloids. But what I want you to get is that within those major categories, you also have subdivisions. So within the metals, there's some metals that are more similar to each other than other metals. You have these families of metals that exist. And within the nonmetals, you have, well, families of nonmetals that exist. And they're very similar to each other. So that's how we sometimes call groups families as well. So metals can be divided into families. The main families or groups for metals are the alkali metals, alkaline earth metals, and then there's also others that we'll discuss. Nonmetals can be divided into families. The main ones that we're going to discuss are halogens and noble gases, and there's others, but those are the main ones we discuss. So these are the main groups or families that we can further divide the classes into because they're even more similar than all the other metals, than other metals together. So again, elements within the same family will have very similar chemical and physical properties. And a big part of that has to do with the number of valence electrons that they have within a group. So you do need to know the properties of the various families and groups. The first one I want to go over are the alkali metals. They are in group 1, except for hydrogen. Remember, that's a non-metal, so that's not an alkali metal. So lithium, sodium, potassium, so on and so forth, going all the way down, those are alkali metals. And one really neat property about them is that they're very, very reactive with water. And they're very soft. You can actually cut them with a knife. So it's almost like cutting butter or cheese or whatever. So they are very soft. They're soft metals. In group 2, part of the metal class, we have alkaline earth metals. So any metal you see in group 2 here would be considered alkaline earth metals. They have 2 valence electrons, so that's important to understand. And I should go back here. Our alkali metals have 1 valence electron. Now, group 2 metals, they are reactive with water and acids as well, but just not as reactive as the alkali metals based on the number of valence electrons. And they're not as soft as alkali metals either. They're actually harder than alkali metals. So these are some typical common properties you'll often hear about the metals in group 2. But they are very similar to each other. Group 2, so beryllium has similar properties to magnesium, to calcium, so on and so forth, all the way down. And then in group 1, lithium is similar to sodium, similar to potassium, so on and so forth. Now, we're not really going to talk about too much about these ones here. These are called the transition metals. You might remember them from grade 10. A lot of them had multiple charges, like copper could be plus or 2 plus, iron 2 plus or 3 plus, so on and so forth. So just remember that they're a bit different. They have different characteristics overall, a little bit more difficult to predict, but they are also groups 3 to 12. Let's just say special groups of metals that have different behaviors, and you'll learn more about that in the future. Now we can go take a look at some families of nonmetals. So halogens, they're group 17. They have 7 valence electrons. So any element in group 17 would be considered a halogen, typically with the exception of At, because that is a metalloid. But some sources will consider it a halogen. So it doesn't really matter too much for our course. We're going to focus on these main ones over here as our halogens. And these are the more reactive nonmetals. So they're the extremely reactive nonmetals. And noble gases, they're in group 18. And these ones here, they have a full valence shell. So they are full valence shell. So they are rather inert. They're unreactive because if you remember, the goal of any atom is to get a full valence shell. And since they already have their full valence shell, they're not really going to react very often. So they typically have 8 valence electrons or 2 if you're helium. So I'm just going to write down full valence shell, anything in group 18. And one neat thing about them is they'll often glow when you pass electricity through them. So you might have heard of neon lights. Neon lights, if you put, basically you have these tubes filled with noble gases, you run electricity through them, and then they start to glow, which is a very cool property. And you've seen them. If you've ever seen a sign that says open or closed on a store window, that would be an example of gases in there with electricity going through them to make them glow. So here you can see our summary. We've seen the 3 classes of elements. We've seen the metals. We've seen the non-metals, including hydrogen on the left side here, and the metalloids. And over here, we've seen that within the classes, you can also have groups of elements. So we have group 1 are alkali metals, group 2 are alkaline earth metals, 17 and 18 are families within the non-metals. So we have the halogens and noble gases, and then we have transition metals as well. They're a little bit different. They often have our multivalent elements in there with the multiple charges. There are other families. So for example, we have a family over here here, here, here. And we typically call those based on the element that's found at the top. So, for example, boron family, carbon family, nitrogen family, oxygen family. But really, we focus primarily on 1, 2, 17, 18. And then we do go into a little bit of detail on transition metals at some point later on. So here are some more learning goals and practice problems that you can try out for yourself based on the lesson.